Hello everyone, today we're proving the uniqueness of a limit. How to prove it? Well, by contradiction. So we start by assuming that the limit as x approaches x naught or some function f of x exists and it is L1. But if we're proving that the limit is unique by contradiction, we have to say that, okay, there are different values the limit can have, and we're assuming that the limit as x approaches the same value, so basically the same limit has a different value. In this way, by contradiction, we'll see that this is not the case, or at least L1 equals to L2. Now, what is the first step in our proof by contradiction? Well, let's just use the definition of a limit for those two cases. Assuming, remember, this is the first assumption. I'm writing the assumptions here. L1 is not equal to L2. That's our first assumption in the proof. Always keep track of assumptions because it's very important to know the assumptions you have when you're proving something, what you're assuming. So let's keep track of them here. Now, by definition, the first line, the first statement means that for every neighborhood V of L1, L1 could be infinity, minus infinity, or a real number, doesn't really care because this is a general definition. So for every neighborhood V of L1, there exists another neighborhood of, I'm calling it U1, a neighborhood of X0. Also X0 can be infinity, minus infinity, or a finite number, such that X belonging to U1 intersection the domain of the function. Remember, x is the domain of the function because f is a function from x contained in R to R. So this is what we're doing here. X belonging to U1 intersection x minus, we're removing the point x0 from this set, implies that f of x, I'm writing it, yeah, I need some more space, implies that f of x belongs to V. I'm writing it here because there is not enough space. F of x belongs to V1. And by V1, I mean V of L1. This is not just notation, and it is useful notation. This means that for every x contained in this set, f of x belongs to V1. If you're not familiar with this, I made another video on my channel, so it's the previous video basically in this video series, so you can check it out. Now, let's go on and do the same for the second limit. This means that, by definition, for every neighborhood V2 of L2, there exists a neighborhood of X0, another neighborhood, such that x in this set U2, in this neighborhood, intersection x minus the point x0, implies that f of x belongs to V2. Okay, it seems messy, the first step, but it's just what we mean by these two things. So this is the first part in the definition. Now, this the limit as x approaches x0 of f of x equals S1 means that for every neighborhood of L1, for every means no matter which neighborhood you choose, it has to work. So this is the first important statement. For every means that we can pick any any V1 has to work. And the same goes for V2, because this works for every V1. It has to be true for every V1, for every V2. So we can, if the proof is not valid for some V1 and V2, then it's wrong. Basically, the statement, the initial statement is wrong. So this is how we base in our proof. This has to work for every V1 and V2. So we can choose a special case. We're assuming that, I'm writing it in red, so it's clearer. V1 intersection V2 equals to the empty set. Now, you may think that we're not proving a generalized version of this theorem, but this is not true, because again, this has to work for every V1, for every V2, so it has to work for V1 and V2 such that those two, the intersection of those two, are equal to the empty set. So bear in mind that this is not a special case. We're still working in the most general situation possible. Now, those two sets being equal to the empty set, this is a property of neighborhoods. For the final case, you can think of it in the following way. This is L1, this is L2. We can pick a neighborhood such that L2 is contained in L1, but we can also pick a neighborhood like this. And you see, the two don't have elements in common, so their intersection, so the intersection means the elements common to both sets is empty. There are no elements common to those two. Okay, now, if those two sets are disjoint, meaning they don't have elements in common, meaning this statement here, we have two different f of x's belonging to one to V1 and the other to V2. But let's look at these statements here. I'm rewriting them here so you can see it more clearly. F of x belonging to this V1. Let's say, let's remove the indexes here because it's general again. Now we call in V1 and V2 those two neighborhoods such that their intersection is the empty set. So f of x belonging to V1, f of x belongs to V1 when x belongs to this set. And this statement is the same as this one. We're saying basically that every x containing U1 intersection the domain of the function minus the point x naught implies this. This means that for every x, no matter which x we choose in this set, we're going to get f of x. We're getting f of x belongs to V1, and this is clear, hopefully. And the same is for for V2. F of x belongs to V2 if for every x in U2 intersection x minus x naught, we have this. So this has to work for every x. But notice that U1 of x naught is a neighborhood of x naught, of course, and so is U2. Also U2 is a neighborhood of x naught. But since the two are neighborhoods of x naught, also the set U1 intersection U2, this is also a neighborhood, and this is also a neighborhood of x naught. So if those two are neighborhoods of x naught, this is also a neighborhood of x naught, and this is a property of neighborhoods. Again, you can see it more clearly if I write, if I just draw the real line and I put x naught here. This is a neighborhood U1. This is a neighborhood U2, for example. and they basically, one is contained in the other, one belongs to the other, and if we take the intersection of the two, it's basically the smaller neighborhood between the two. So this is clear, and this also works for when x naught is infinity or minus infinity. So from this property, if those two are neighborhoods of x naught, so 2 is u1 intersection u2. Now, this being a neighborhood of x naught, well, it's not clear yet, because we have another thing that is very important and often misunderstood, that x naught is an accumulation, limit, or cluster, whatever you want to call it, point of the domain of the function. It means that x naught, remember, is an accumulation point of the set x, means that a neighborhood of x naught intersection x minus x naught is not equal to the empty set, meaning it contains elements, and this is true for every u of x naught. What we're saying here is that x naught is an accumulation point, which is by the definition of a limit, if for every set, for every neighborhood u of x naught intersection x minus the point x naught, so we remove x naught from the interval, is not equal to the empty set. This is true for every u of x naught. But since this is true for every u of x naught, this has to work for u1, and it has to work for u2. This means that this set and this set are not empty, and since also u1 intersection u2 is a neighborhood of x naught, we also have that x naught is an accumulation point, so u1 intersection u2 also intersection x minus x naught is not equal to the empty set. Now, this seems strange, I know, but we know that x naught, by assumptions of basically when we start defining a limit, we require x naught to be an accumulation point of x. An accumulation point of x, by definition, is for every neighborhood of x naught, u of x naught intersection x minus x naught is not equal to the empty set. And since those two are neighborhoods of x naught, also their intersection is a neighborhood of x naught. And since this neighborhood, this intersection is a neighborhood of x naught, and this is true for every neighborhood of x naught, this quantity must be different from the empty set. And this is important because the intersection of two sets being different from the empty set means that there are elements in common, at least one element, and that element has to be different from x naught and have to be different from the values not defined, so that don't live in the domain of the function. This means that there exists a point x. I'm putting just an arrow, a line on top of it, so we don't mess up. There exists a point x, at least one point x, such that it belongs to both u1 and it belongs to u2, because this is not empty. We don't consider x naught, we don't consider points that really don't care because they're not in the domain of the function. So this point here that belongs to both sets has to be in x, and this point is not x naught, because we're removing x naught. But now, let's take a look at the definition here, or maybe this line. A point that belongs in U1 implies that f of that point belongs to V1. This means that f of x, the little arrow on top, belongs to V1, but this point also belongs to U2, and this means that f of x of this point, so x with the line on top, belongs to V2. But this number belonging to both sets means that their intersection, so I'm writing it here, their intersection, V1 intersection V2, is not equal to the empty set, because there is at least an element f of x that is common to both sets. So their intersection cannot be equal to the empty set. It can be equal to the set containing only this element, but the important thing is that it is not equal to the empty set. But look at this. We started with this statement that the intersection of these two equals to the empty set, and we arrived at, okay, the intersection of these two is actually different from the empty set, it's not empty. This is a contradiction, and this contradiction comes from this first assumption that those two limits are different, because if they are different, there exist two intervals V1 and V2, two neighborhoods of that point, of those points, such that their intersection is empty, because they're not the same point, they're two different points, so we can choose two neighborhoods that are just separated from each other. So this is a contradiction. This contradiction comes from this fact, and therefore, for those two statements to be true for all V of L1 and V of L2, L1 must necessarily be equal to L2. So if a limit exists, this is one of the assumptions, then the limit is unique. There can't be other values. So the limit is unique, and hence we can conclude the proof with a little drawing of a box, or maybe whatever you want to. I prefer the little box. I mean, it's more satisfying. It's the most satisfying to draw when you finish a proof. And this is a rigorous proof, and yes, that's all we're doing today. If you enjoyed the video, please subscribe to my channel, share this video with your friends, your classmates, and what else to say? And I don't know, just leave a comment in the comment section about something you want to see in the future on my channel. And this is all. That's all for today. Hope you enjoyed the video, and see you next time. Bye.